permutation is a rearranging of elements. So with our Z3 group, which includes 0, 1, and 2, there are 3 factorial possible permutations. Factorial simply means 3 times 2 times 1. Every time we add a group element, there are many more permutations possible. 4 factorial is 24. If we go up to 12, it's almost 500 million different combinations of group elements. So it really increases the number quite a bit. Now, the identity element E, when we add it to any group element, it results in the same element. So this first permutation is not really a rearranging of elements. We use this Cauchy notation right here in the big parentheses. The starting order followed by the ending order, so it's the same. Now alpha, operation alpha represents 0 going to 1, 1 going to 2, and 2 going to 0. Or in Cauchy notation it looks like this: 0, 1, 2, 1, 2, 0. And then alpha squared, we see the following permutation. Now let's take a look at this geometrically for a minute. Using an equilateral triangle with these 3 elements, 0, 1, and 2. Now, it doesn't change with the identity element. With alpha, though, what do we need to do in order to obtain this permutation? Well, this represents a rotation. So now, rather than 0, 1, 2, we have 1, 2, 0. Alpha squared, similarly, is just twice that. So we do 2 rotations, and we end up with 2, 0, 1. Now, since there are 6 permutations, how do we obtain the other 3? Well, if we look at the other permutations, beta, one other thing real quick. The first 3 permutations actually represent the 3 rows in a Cayley table. If we look at here, 0, 1, 2, 1, 2, 0, and 2, 0, 1. So it's kind of interesting. Now the beta operations, these are different. We can't just keep rotating our group in order to obtain this sequence. So if you notice a pattern here, each of the final 3 permutations, one group element stays the same while the other 2 are swapped. 0 stays while 1 and 2 are swapped. Beta alpha, 1 stays the same while 0 and 2 are swapped. And beta alpha squared, 2 stays the same and 1 and 0 swap. Now geometrically, this is what has to happen in order to obtain those permutations. If we have our starting elements, 0, 1, and 2, beta would represent a line of symmetry across over 0, which keeps 0 where it is and swaps 1 and 2, so we have 0, 2, and 1. Beta alpha, similarly, we could either look at it as a line of symmetry over 1, which keeps 1 and swaps 2 and 0, or beta followed by alpha, which is a rotation. It gives us the same permutation. And then finally, we can either have a line of symmetry over 2, which gives us the following permutation, or this operation beta followed by alpha squared. So we have 1, 0, 2. So next we'll look at the musical application of permutation groups.